We're now on to Chapter 3B PowerPoint, which still has to do with temperature and humidity extremes, all right, but now we're going to be perhaps a little bit more practical. I know I threw a lot of highfalutin science at you during the last PowerPoint, but now we get down to the bottom line, which is weather extremes and human comfort or discomfort. It's that sensible heat that you feel, or lack thereof, when you walk out the door in the morning. Look, everybody wants to look at the weather in the morning to find out, hey, what's it going to be like outside? What's the high temperature going to be? So you can dress appropriately. The human body's perception of temperature is called sensible heat. Now, we don't have brutally cold winters here near sea level in the San Joaquin Valley, but many other places in the U.S. do, as you very well know. Now, when it comes to wind and cold, our bodies do feel colder when the wind blows because the moving air removes the thin layer of warm air molecules that form very close to our skin. That's dangerous in extremely cold conditions. That's why we bundle up in the wintertime, essentially. So the National Weather Service, along with other agencies, developed what's called the Wind Chill Index, or WCI, which gives us an idea of how the combination of low temperatures plus the wind feels to unprotected skin. High winds and below freezing air can so rapidly move heat from the body that extremities in the body, like your toes, your fingers, can freeze and discolor, and this is what we call frostbite. The following slide shows Table 3.3 from Chapter 3, which shows the wind chill index in miles per hour and degrees Fahrenheit. There's also one in your book that shows kilometers per hour and degrees Celsius, but this is the more common one we would use in the United States because we still publicly issue weather information in degrees Fahrenheit here in wind speeds in miles per hour. This is that very chart. So for instance, if you have a wind speed of 30 miles an hour and an air temperature of 25 degrees above zero Fahrenheit, that gives you a wind chill index of 8. That's what it feels like, 8 degrees above zero Fahrenheit to unprotected skin. Now let's switch to not cold, dry weather, but cold, damp weather. A cold, rainy day often feels colder than a dry day. That's because water and exposed skin conducts heat away from your body much more efficiently than dry air does. The rapid loss of body heat may lower the body temperature below its normal level, and if this is sustained for a dangerously long period of time, it produces what we call hypothermia. That is the rapid, progressive mental and physical collapse that accompanies the lowering of human body temperature. Now, that's why every May and June, when the rivers run high with the snowmelt, they warn people, yeah, it's a hot day, but don't be foolish and jump into a swirling river to cool off, because if you get caught down there in the riverbed, hypothermia takes over and you can't get out of the water. It's very, very dangerous. The general concept of humidity is often a complicated one, so we're going to kind of cut through it all here. Humidity is a very important factor in human comfort. Your body cools off by emitting infrared energy and by perspiration, okay? The perspiration is supposed to evaporate off of your skin, and if it evaporates rapidly off your skin, then you feel that sensation of cooling off. If the perspiration on your skin evaporates more slowly, then it causes people to feel hotter. It evaporates more slowly if there's already a whole lot of moisture in the air. If the air is saturated or very close to being saturated, combined with very high temperatures, high heat, that produces uncomfortable conditions because this is not conducive to that perspiration evaporating from your skin. Yeah, it may be hot here in the valley in the summertime, but be thankful that heat is dry with low humidity. Be thankful it's not like 95 degrees with 60% relative humidity. That's very uncomfortable. Relative humidity is a complicated concept, but we'll try to sort it out for you here. The most common way to analyze the amount of humidity in a parcel of air is called relative humidity. It's actually just a ratio, like a percent, of the actual amount of water vapor in the air relative to the maximum amount of water vapor in a blob of air, a parcel of air, required for that blob of air to become saturated at a particular temperature and pressure. It's a very simple ratio. So you can then see the water vapor molecules are relative to the regular dry air molecules. So it's a ratio, and it's expressed in percent. How can relative humidity change? Well, If the moisture content of the air stays the same and the temperature increases, relative humidity decreases. If the moisture content of the air stays the same and the temperature decreases, then relative humidity increases. So we see a daily or diurnal cycle where on a typical clear day, relative humidity is lowest in the afternoon at the hottest part of the day. That's the dip in the green graph there. And then when the green graph soars upward toward daybreak, that's because the temperature has fallen, but the moisture content of the air stays the same, and that's when relative humidity is high. These changes occur daily, meaning diurnally, and seasonally, from place to place and from time to time. So given a clear day, all things being equal, midnight to midnight, relative humidity is highest at daybreak and lowest at the hottest part of the day. The dew point is the temperature to which the air would have to cool down to in order for the air to become completely saturated, meaning 100% relative humidity. If you have high dew points, that indicates that you have high water vapor content in your blob of air. If you have low dew points, which we typically do around here, especially in summer, and sometimes in the winter, that means you have a low water vapor content of the air. When the air temperature and the dew point are far apart, the relative humidity is low. A typical summer day in Fresno, the temperature might be 100 and the dew point might be 50. That means a relative humidity of about 25%. When the relative humidity is high, that means the temperature and dew point are very close to the same value. For instance, on a foggy morning in Fresno, if the temperature is 40 and the dew point is 40, that means you have a relative humidity of 100%, and there's a high probability that if you look out the window, you're going to see fog on a winter morning with a temperature and dew point both at 40 degrees Fahrenheit. Dew points in the United States rarely exceed 80 degrees Fahrenheit, and that's a good thing because the higher that dew point, especially in a hot day, the more uncomfortable you're going to be. Now let's have a look at 2 days of data, which is actually from the Fresno Air Terminal. From 3 o'clock Wednesday afternoon, December 26th last year, to 2 p.m. Friday, December 28th, 2012. If you look at the two graphs on the left, you notice how the red line, as the temperature and dew point are farther apart. In the afternoon, the red line goes up. You notice the dew point doesn't change much. It goes from the 40s to the, upper 20s to lower 30s. But as the red line goes up, relative humidity goes down. That's the graph in the middle. As the temperature goes down, close to the dew point, the relative humidity goes up. This is courtesy National Weather Service in Hanford, California, but this is data from the Fresno Air Terminal for December 2012. Here is a look at average surface dew point temperatures from January and July across the United States. Notice the west is generally dry. If you look at January, our dew points are generally in the 30s to lower 40s here. And if you look at July, generally speaking, our dew points are in the 50s. The high dew points, of course, are in the summertime in the southeastern United States, where the combination of heat and humidity can often make things very, very uncomfortable along the Gulf of Mexico coast of the southeastern United States. Relative humidity in different seasons. Now, this is an interesting concept. If you look at, say, polar air, if the temperature is 28 degrees Fahrenheit and the dew point is 28 degrees Fahrenheit, the relative humidity is 100%, even though there's not much moisture in the air, because cold air really can't hold very much moisture. And so in that picture on the left, you see fog formation. I think that looks like Yosemite Valley, if I'm not mistaken. But then if you go to the summertime in the dry desert southwest, even with a higher dew point, compared to the picture on the left, you've got a temperature of 95 and a dew point of 50. That still makes a relative humidity of 21%, because relative to the amount of air, that amount of moisture that dry hot air can hold, the relative humidity is lower, because the temperature would have to fall all the way down to 50 in the example on the right for 100% relative humidity to occur. Now, this is something that it's kind of a myth. You call it an urban myth, call it a rural myth, doesn't matter, that I'm going to debunk here. There is a perception that humid air is heavy. It's not. If you took two equal blobs of air and one of those blobs of air had more water vapor in it than the other, the blob of air with the most water vapor would have more buoyancy. It would be less in mass and weight, because if you look at hydrogen on the periodic table, it's number 1, right? And if you look at oxygen, it's number 8. So the more water molecules you have in your volume of air, the less heavy that air is going to be and the more it's going to rise. That's why we have cloud formation. So the bottom line is humid air is lighter than dry air when comparing equal volumes next to each other. It's hard to remember, but if without that physical occurrence in Earth's atmosphere, we would not have cloud formation like we do. Our atmosphere would be completely different. Humid air and dry air do not weigh the same. Humid air weighs less than dry air. Now this goes to something called the heat index, or more appropriately known as the temperature humidity index, which combines air temperature with the relative humidity to determine what we call an apparent temperature that the body feels, so to speak, for various combinations of air temperature and relative humidity. The higher the combination of high heat and high relative humidity, the higher that apparent temperature is and the more uncomfortable you feel. Here is that heat index, or temperature humidity index. So let's say that the air temperature is 105, all right, and the relative humidity is 35%. That 105 feels more like 118 on the chart. So this is what we mean by apparent temperature. Typically around here in Fresno, let's say that the air temperature is 100 degrees Fahrenheit and the relative humidity is 20%. That means that 100 actually feels like 99. How about that? 1 degree cooler. So that's the apparent temperature, what your skin feels with the combination of heat and humidity or lack thereof. So moving on to the health effects that can occur based on a dangerous combination of heat and humidity. The table 3.5 on page 87 shows the different categories of the heat index or temperature humidity index and the related heat syndromes. Remember, way back in chapter 1, if you rewind your mental DVD for a moment, we discussed that heat is the #1 weather killer in the United States. Heat's very, very dangerous. No question about that. Let's talk a little bit about the infamous July 1995 Chicago heat wave. There were more than 700 people that died in that heat wave. Nighttime temperatures did not cool off much during the peak of that heat wave because dew points exceeded 80 degrees Fahrenheit on at least 2 nights. The next slide, which is table 3.7 in your book, shows the minimum and maximum temperatures during that week. And you can see how once the hottest period occurred and it started to be a little less hot, you notice how the deaths went up. That's because it was kind of a delay of the people's health effects because of this terrible heat wave. And you heard the expression, it's not the heat, it's the humidity. Well, in this case, it certainly was the humidity, because when the dew points don't go below 80, it doesn't cool off at night, even with the sun having set. There was a terrible heat wave in Europe in August of 2003. You may remember that from the news. It especially hit France hard. There were about 35,000 people that died throughout Western Europe in this heat wave, maybe as many as 52,000 because of the delayed reaction. 15,000 people in France alone. And you can see the record high temperatures that occurred in these countries in degrees Fahrenheit. Amazing that France got up to 111 in the south of France, and London got up to 101 degrees Fahrenheit, which was just extraordinary. This chart comes from a book called Severe and Hazardous Weather by Robert Walsh and Charvelot, 3rd edition. And it shows the departures from average summer temperatures in degrees Celsius in France from 1901 to 2003. And you really can see that spike going up in 2003. A large departure from average summer temperatures. That was an astounding heat wave in Europe, and now they're a lot more conscious of this if it should happen again. So this ends Chapter 3 with the Chapter 3b PowerPoint on temperature and humidity extremes.